So in 1.1, we just reviewed what a function was. We looked at domain and range, and we looked at the x and y intercepts. In 1.2, we're going to talk about additional features of these function graphs. So we're going to look at how do we find where a function is increasing and decreasing? How do we find where it's positive and negative? And then we're going to talk about this end behavior. So what we're going to do is we're going to look at one feature at a time, and then we'll practice it. So like we will do positive and negative and then practice, then we'll come back and do this and practice, and then we'll do this. So starting with positive and negative, what we are looking for here is the interval for wherever the graph is either above or below the x-axis. So a function is positive when the graph lies above the x-axis, and a function is negative when its graph lies below the x-axis. So if we think about like the x-axis is sea level, well, obviously any height above sea level would be positive, and any height below sea level would be negative. So think about that. Where it's positive, it's where is it above the x-axis, and where is it negative, where is it below. So when you are looking to describe the intervals, like when the question says what's the interval for which this graph is positive or which this graph is negative, on the x-axis, you want to be looking for the x-intercepts. So look for the x-intercepts. Because wherever that graph intersects the x-axis, that's obviously where it goes from being one to the other. So this graph was negative until -2, and then it's positive in between these two x-intercepts, in between -2 and 0. Then it's below the x-axis between 0 and 2 until it comes back above the x-axis, which would be for anything greater than 2. Okay? So when we write these intervals, we're going to write them using our inequality notation and our interval notation. So if we looked out at these practice graphs, number one, if we're trying to identify where that graph is positive and negative, well, this graph has two x-intercepts. One at -3 and one at +1. This is where the graph is positive. This is where the graph is negative. So what we're doing with positive and negative is looking above and below the x-axis. That's what that means. So this graph is negative here and here. It's negative in two different places. It's above the x-axis. It's positive in between these two places. So all we need to do is be able to use our inequality notation or the interval notation to describe where is this negative and positive, meaning it's negative from the x value of -infinity all the way to -3. Then it's positive in between -3 and 1. And then it goes negative again from that +1 all the way to x equals +infinity. Okay? So again, it was positive in between -3 and 1. So if I was at -3 and at 1, it's at sea level. It's at 0. It's neither positive or negative. So they're not going to be included ever. All right? And then it's negative in two different spots. So it's negative, like I said, for the x values all the way from negative infinity to the -3. But instead of writing both of these as a compound inequality, because again, it was negative here, but then if I wrote the inequality for this half, it would be wherever 1 is less than x, which is less than the positive infinity. So instead of writing these two separate compound inequalities, I'm just going to write it as 1. Anything less than -3 is going to be negative. And then any of my x values greater than 1 is where my graph is below the x-axis. So 1 is a little easier because it looks like we've got two x-intercepts, but what does it do here at that 0, 0? It stays below, right? So really, it's negative or positive here. And then it's negative anywhere here. So we only have one positive interval and one negative interval. We only have one place that we need to worry about describing where is it above, and only one place where we'll describe where it is below the x-axis. Okay? So it's positive all the way from negative infinity to this point at -3 again. So when we write the point, I would use that same x-intercept to describe where it's negative, because now it's below the x-axis from -3 all the way to positive infinity, because it's going to stay below. And this one's the easiest because we've got an exponential graph, which remember with exponential graphs, they approach this horizontal asymptote, which means a line that they get closer and closer and closer to, but they never cross. So if we're looking for an x-intercept, will we ever have an x-intercept? No, because it's never crossing the x-axis, which means this graph is always positive. Every piece of this graph is going to be above the x-axis. It's always positive, right? So any x value from negative infinity to positive infinity, it's going to be above the x-axis. So this makes it really easy for us to look at. Now that we've talked about positive and negative, we're going to talk about increasing and decreasing. And this is just, where is your graph moving up? Where is your graph moving down? So a graph or a function is increasing when its graph moves up as x moves to the right. And a function is decreasing when its graph moves down as x moves to the right. So anytime we read a graph, we're always going to read a graph from left to right. So as you're moving to the right, what is the graph doing? So if I started at the furthest left part of my graph and I were to trace it with my finger would be moving up until right here, and then I'd go down until right here, and then I'd go back up. So this graph is increasing in two places and decreasing in one spot. So what you are looking for when you are describing these increasing and decreasing intervals are going to be any maximum or minimum points. So you're looking for like those mountains and those valleys. Where are their turnaround points? So in this case, we had a turnaround point right here, which is why it went from blue to red. And then we go from red to that blue, so that's another turnaround point. So when you're describing increasing and decreasing, that's what you're looking for. Where are those turnaround points? And again, we're concerned with where are those turnaround points on the x-axis. Every time we're describing these intervals, we're always describing them in terms of x. Okay, so you're always looking at their x value. So let's practice. Oh, it's at the bottom here. All right, number one, we've got our quadratic. So looking at this graph from left to right, if I were to trace it, I'd be going up until the vertex and then right back down. So this point right here is going to be our turnaround point that we need to focus on its x value. It has an x value of -1. So when we're describing our intervals, we're using -1. So it was increasing all the way from x equals -infinity until x equals -1, and then it decreases after -1 all the way to x equals +infinity. All right, so we will write those intervals just like that. Graph number 2. Graph number 2, if we look at it from left to right, we start going down right until this point that has an x value of -2. So we're going down until that point. Then it turns around and it goes back up until x equals 0. And then at x equals 0, it begins to decrease again. So this time we're going to have 2 decreasing intervals and 1 increasing. So our increasing interval is going to be the easiest because it's between -2 and 0. So when you write that as an inequality, your minimum value is -2, your maximum value is 0. So between -2 and 0 is where it's increasing. So it was decreasing from -infinity all the way until -2. And then it was decreasing again from this 0 all the way to infinity. So when I write that, you could write it like that as the inequality notation, or this is when I just like to write it as one inequality because I just say anything less than -2 is where it was decreasing. So our exponential graph, if I look at it from left to right, are there any turnaround points? No, which means it's not going to have both an increasing or a decreasing. As I look at this from left to right, it's always going to be increasing. So characteristic we're going to talk about is end behavior of a graph. So the end behavior of a function is the behavior of the graph as x approaches positive or negative infinity. So when we're looking at x approaching positive infinity over here, we are looking at the right side of the graph. So as x approaches positive infinity, the arrow on the right side is pointing up, which means my y is approaching positive infinity. Then this notation means as x is approaching negative infinity, so negative infinity is going to be over here, which is the left side of the graph. So look at the arrow on the left side. It is pointing down, which means as my x is going towards negative infinity, my y is also approaching negative infinity. So as x approaches positive infinity, what's the right arrow doing? As x approaches negative infinity, what's the left arrow doing? If it's pointing up, that means y's are going to positive infinity. If it's pointing down, it means y is going to negative infinity. Okay? So let's practice. I think if I look at the left side of this graph, which way is this arrow pointing? Down, which means arrow. Positive infinity would be down here. What's this right arrow doing? It's also pointing down. Graph number 2. Both of those arrows aren't pointing pointing down. They're pointing in opposite directions. So if we start with the left side with negative infinity, look at the left arrow of your graph, and it is pointing up, which means the y is approaching. Well, that right side arrow is pointing down. So that must mean that the y values, the exponential, because as we approach negative infinity, which is this left graph, this arrow is not pointing down. But remember, that's because we can never cross the x-axis. And the equation for the x-axis is y is equal to 0. So the line that this is approaching is y equals 0. So as x moves towards negative infinity, my y values are getting closer and closer to 0. Approaching positive infinity, well, that right arrow is pointing up, which means as we're approaching positive infinity this way, we're going to keep opening up this way. So our y we're describing, we'll start with positive, and I'm going to start with the, we'll put the inequality one on this line, and then we'll put the interval on this line. So with the inequality, write that as an inequality. The minimum value where it's positive was that -3, and that's going to be less than the x, which is less than the maximum value where it was positive, which was 1. You'll notice on these inequality symbols, I did not include the or equal to, because if I wrote this as my interval notation, that's when I would just use the parentheses because it's not included, the minimum value, which was -3, the maximum, which was -1, and then close that parenthesis. Negative is just a tad more complicated, only because write that, like I said, I'm just going to write wherever x was less than -3, or wherever that x was greater than 1. And then we do need to practice writing it in interval notation because you guys could see it both ways. But again, I think interval's easier. We'll use those parentheses, that minimum value, that was that negative infinity, all the way to -3. And then we would use that union sign to represent like the union or, because or it was also negative from 1 to positive infinity. And that 1 is not included and infinity is never included, so we use those parentheses. All right, so that's positive and negative on graph number 1. Now let's look at graph number 2. With that, I'll just do my little compound inequality. It was positive from negative infinity, which is less than x, which is less than the -3. And then the easier way to write it with that interval notation would be with those parentheses, and that would be from negative infinity to -3. And then at that same, so I would just do -3 is less than that x, which is less than the positive infinity. And then if I wrote that using my interval notation, I'm going to use the parentheses because it's not included. The minimum would be the -3 all the way to positive infinity, and then parentheses there. All right, last graph, graph number 3. Write that interval because it's always positive, so you could write all real numbers if you want. Or you could do the negative infinity. I don't want to use the highlighter. Negative infinity, which is less than x, which is less than positive infinity. Or again, all real numbers. And then writing that as the interval notation, that's your parenthesis from negative infinity to positive infinity. Boom, done.
What is that sign you use for the alt?
I do like 2 lines and an R, yeah. 2 vertical lines and then R. So if our graph is always positive, meaning it's never going to cross the x-axis, then it's never negative. So for the negative interval, 1 doesn't exist, so does not exist. If it's always positive, that means it's never negative. So that DNE just means like it does not exist. There is no negative interval. Okay. Next characteristic that we are going to... it was increasing from negative infinity all the way till -1. And so then if I write that with interval notation, from negative infinity all the way to -1, and you've got those parentheses. And then it was decreasing after that. So now it's decreasing from -1 all the way to positive infinity. So now our -1 goes first, which is less than x, which is less than our positive infinity. And so in that interval notation, -1 is the lowest number where it starts to decrease. Positive infinity is the highest, and then both of those get parentheses because that turnaround point isn't included. It's not increasing or decreasing right there. Kind of stalls and then back down. All right, so let's practice that same thing with... So that would be from -2 all the way to 0. And if I wrote that, it would be -2, 0. Now it's decreasing in 2 spots, which means we're going to have kind of this union orientation, this or, to show that it's decreasing in 2 places. So when I write this, I'll just say wherever x was less than -2 or where x was greater than 0. And so then when I do my notation, my interval notation, I would do from negative infinity to -2, and then do the union sign again from 0 to positive infinity. All right. The last one gets easier again. Yay for an exponential graph. Only has an increasing interval, and this would be very similar to where it's positive because it is increasing for all real numbers, all the way from negative infinity to positive infinity. And if it is always increasing, then a decreasing interval does not exist. All right, we're so close. Last starts with negative infinity. Yeah. So as x approaches negative infinity, which means I'm looking at the left arrow, my y values are also approaching negative infinity. And then as x is approaching positive infinity, which is the right side of the graph, the right means y is approaching negative infinity. So the end behavior for both sides of that graph is negative because both those arrows are pointing down. All right? If I, because that's what's here first, positive infinity. And then as x approaches positive infinity, so now I'm looking at the right side, approaching negative infinity. Very good. All right, last one, and we're going to save this one for later. This is the very last one. This one's kind of unique, though. So y values are approaching 0 because of that asymptote. And then on the right side, as x values are approaching positive infinity. Woo! Told you that was a lot today. Okay.